Download this code from codegive.com, link in the description below. Zero-shot video understanding, a comprehensive guide with code examples. Zero-shot learning, ZSL, is a fascinating field of machine learning that aims to recognize objects or concepts it has never seen before during training. This is achieved by transferring knowledge from seen concepts to unseen concepts using auxiliary information, typically semantic embeddings. In the context of video, zero-shot learning allows us to classify video clips into categories for which we have no labeled training data, relying instead on our understanding of relationships between video features, text descriptions, and semantic spaces. This tutorial will provide a deep dive into zero-shot video understanding, covering essential concepts, common approaches, code examples using Python and popular libraries like pytorch and transformers, and best practices for building effective zero-shot video classification models. 1. Understanding the core concepts. Before diving into the code, let's establish a solid understanding of the fundamental concepts involved in zero-shot video understanding. Scene classes, training classes. These are the video classes for which you have labeled training data. The model learns to extract visual features from these videos and associate them with semantic representations of their corresponding classes. Unseen classes, test classes. These are the video classes for which you have no labeled training data. The goal of zero-shot learning is to classify new video clips into these unseen classes based on the knowledge gained from the seen classes. Semantic embeddings. These are representations of classes in a high-dimensional semantic space. These embeddings capture the relationships between different classes. Common methods to obtain semantic embeddings include using word embeddings, word2vec, glove, fast text. These represent words as vectors, capturing semantic similarities. We can use the word embeddings of the class names directly. Sentence embeddings, SentenceBird, universal sentence encoder. These encode entire sentences into vectors, allowing for richer semantic representations. We can use descriptions of the video classes to generate sentence embeddings. Knowledge graphs, WordNet, ConceptNet. These represent concepts and their relationships in a graph structure. We can derive semantic embeddings from these graphs. Visual features. These are representations of the video content extracted by a visual feature extractor. Common methods include CNN-based feature extraction, using pre-trained CNNs, example ResNet, VGG, on individual frames or short clips to extract spatial features, then pooling or aggregating these features. 3D CNNs, extending CNNs to 3D, allowing them to learn spatiotemporal features directly from video volumes, example C3D, I3D. Transformer-based video encoders, utilizing transformer architectures, such as Timesformer or Videobird, which are capable of capturing long-range temporal dependencies in video sequences. Mapping function, a function that learns to map visual features from videos to the semantic space. This is the key to transferring knowledge from seen to unseen classes. Common approaches include linear regression, a simple mapping function that learns a linear transformation between the visual feature space and the semantic space. Neural networks, example multi-layer perceptron, more complex mapping functions that can capture nonlinear relationships between the visual and semantic spaces. 2. A step-by-step approach to zero-shot video classification. Here's a breakdown of the general steps involved in building a zero-shot video classification system. 1. Data preparation. Gather video data. Collect video clips for your scene classes, training data. You do not need video data for your unseen classes. Asterisk define seen and unseen classes. Asterisk clearly define which classes will be used for training and which will be used for testing the zero-shot capability. Asterisk obtain semantic embeddings. Asterisk generate semantic embeddings for both seen and unseen classes using a suitable method, example sentence bird, word2vec. 2. Visual feature extraction. Asterisk choose a visual feature extractor. Asterisk select a suitable pre-trained model, CNN, 3D CNN, or transformer, based on your data and computational resources. Asterisk extract features from videos. Asterisk process your training videos using the chosen model to extract visual features. 3. Mapping function training. Asterisk choose a mapping function. Asterisk select a mapping function, linear regression, neural network, to map visual features to the semantic space. Asterisk train the mapping function. Asterisk train the mapping function using the extracted visual features and the corresponding semantic embeddings of the scene classes. The goal is to learn a function that predicts the semantic embedding of a video based on its visual features. 4. Zero-shot classification. Asterisk extract visual features for test videos. Asterisk extract visual features for your unseen class videos using the same feature extractor used in training. Asterisk predict semantic embeddings. Asterisk use the trained mapping function to predict semantic embeddings for the test videos based on their extracted visual features. Asterisk nearest neighbor search. Asterisk find the nearest neighbor among the semantic embeddings of the unseen classes to the predicted semantic embedding of each test video. The class corresponding to the nearest neighbor is the predicted class. This can be done using cosine similarity, Euclidean distance, or other distance metrics. 3. Code example, zero-shot video classification with sentence BERT and a linear mapping. This example demonstrates a simplified implementation of zero-shot video classification using pre-extracted visual features, sentence BERT for semantic embeddings, and linear regression as the mapping function. It's important to note that this is a simplified example, and you'll likely need to adapt it to your specific dataset and needs. Explanation of the code. 1. Data preparation. We define lists of seen_classes and unseen_classes. We create dummy visual features using np.random.rand. In a real application, you would replace this with features extracted from your videos using a pre-trained model like i3D or a transformer-based video encoder. We load the sentence BERT model using sentence transformer. We generate semantic embeddings for the seen and unseen classes using embedding_model.encode. 2. Mapping function training. We create training data x_train, visual features, and y_train, semantic embeddings. We train a linear regression model, linear regression, to learn the mapping between visual features and semantic embeddings. 3. Zero-shot classification. We extract visual features for the test videos, x_test. We use the trained mapping function to predict semantic embeddings for the test videos. For each test video, we calculate the cosine similarity between its predicted embedding and the semantic embeddings of the unseen classes. We select the unseen class with the highest similarity as the predicted class. 4. Evaluation, conditional. This section provides example code on how to evaluate the zero-shot accuracy. You will need ground truth labels for your unseen data to compute meaningful accuracy metrics. It has been commented out as we are using random data. Important notes. Replace dummy data. The key is to replace the dummy data with your actual video features and semantic embeddings. The quality of these features and embeddings is critical for the performance of the zero-shot model. Feature extraction. The choice of the visual feature extractor significantly impacts performance. Experiment with different architectures, CNNs, 3D CNNs, transformers, and pre-trained models to find the best one for your data. Semantic embeddings. Choose a semantic embedding method that captures the relevant relationships between your classes. SentenceBERT is generally a good starting point, but you may need to explore other options depending on the nature of your classes. Consider fine-tuning the SentenceBERT model on a task relevant to your video classes for improved performance. Mapping function. Experiment with different mapping functions, linear regression, neural networks. Neural networks can learn more complex mappings, but they also require more data to train effectively. A simple MLP, multi-layer perceptron, is often a good choice. Normalization. Normalizing visual features and semantic embeddings can improve training stability and performance. Evaluation metrics. Evaluate your zero-shot model using appropriate metrics, such as accuracy, precision, recall, and F1 score. 4. Advanced techniques and considerations. Attention mechanisms. Incorporating attention mechanisms can help the model focus on the most relevant parts of the visual features when predicting the semantic embedding. Graph neural networks, GNNs. If you have a knowledge graph representing the relationships between your classes, you can use GNNs to refine the semantic embeddings or to learn a more sophisticated mapping function. Adversarial training. Using adversarial training techniques can help the model learn more robust and transferable features. Domain adaptation. If your training and testing data come from different domains, you may need to use domain adaptation techniques to bridge the gap. Handling ambiguity. Zero-shot learning can be challenging when there is significant ambiguity in the visual features or the semantic embeddings. Consider using techniques to disambiguate the representations. Computational resources. Training deep learning models for zero-shot video understanding can be computationally expensive. Consider using GPUs and cloud computing resources. 5. Best practices. Start simple. Begin with a simple architecture and gradually increase complexity as needed. Experimentation. Thoroughly experiment with different feature extractors, semantic embeddings, mapping functions, and hyperparameters. Validation. Use a validation set to monitor the performance of your model and prevent overfitting. Data augmentation. Consider using data augmentation techniques to increase the size and diversity of your training data. This could include techniques like temporal cropping, scaling, and adding noise. Error analysis. Analyze the cases where your model fails to identify patterns and areas for improvement. 6. Conclusion. Zero-shot video understanding is a challenging but rewarding field with many potential applications. By carefully selecting appropriate features, embeddings, and mapping functions, you can build models that can classify video clips into unseen categories, opening up new possibilities for video analysis and understanding. Remember to experiment, validate, and iterate to achieve the best possible performance on your specific task and data set. This detailed tutorial provides a solid foundation for exploring this exciting area. Good luck.